Let's go to our final presenter now, and I'll ask Murray Nottle to share his screen while I give him a quick intro. Murray Nottle is a mechanical engineer from the Carnot Group and a lifelong interest in affordable and practical energy efficiency. He's working with compressed air industry for more than 25 years and been with the Carnot Group for over 10 years working on compressed air and other projects. He often works in consulting for other consultants and help them for guidance in compressed air. He certainly, what I know about compressed air, he's already forgotten. And certainly if you're thinking about looking at a new air compressor because your supplier has told you that the only way to fix your air compressor problem is with bigger air compressors, I do recommend you speak to Murray first. But today he's going to talk to us about heat recovery from air compressors. So I'll hand over to you, Murray.
Thanks, Jared, and welcome everyone. I'd like to begin by acknowledging the traditional owners of the land of where I am, the Wurundjeri people of the Kulin Nation, and I pay my respects to their elders past, present and emerging. Yes, today I'll be talking about waste heat from an air compressor to heat water, and I'll be discussing the front-end engineering design to support a Capex proposal. For those of you who have got oil-free machines, I'm sorry, my presentation is focused on oil-flooded machines because that's 90 to 95% of the market, but I can certainly help you with oil-free machines as well. Firstly, about the Carnot Group, we're named after Sadi Carnot, who's a Frenchman who's considered the father of thermodynamics. We're engineering consultants and we work with brownfield sites predominantly. So we troubleshoot old systems, upgrade them, we'll install new plant and equipment and processes. We do data logging, we've got advanced computer modeling in finite element equipment, and our main customers are manufacturing, mining and water utilities. So why doing this presentation now? OEM air compressors have had heat recovery options for over 20 years, but very few have been sold. Now, part of that is because the compressor salesmen only think about selling air compressors, not equipment beyond that, but also because customers have got energy silos and it is too hard to think between the energy silos. Some common experience is that you can only recover 60% of the heat from an air compressor for 60% of the time. Now, I don't know the systems where that's come from, but I suggest it could be a poorly maintained or poorly implemented systems. And there's lots of pitfalls, which we'll hopefully try and steer around a few of that a while ago. I'm getting confused. Jared had talked already about the graphics on the right. These are talking about where the energy prices are going. That was a month or so ago from Tennant Reed. I heard overnight that some of those prices are actually substantially worse, brought on by the current cold snap. And as we've heard, the overseas situation is going to make things a whole lot worse as well. So as I've said, this presentation aims to help sites get approval for a Capex for a well-designed and evaluated heat recovery system. People don't understand what's required inside a compressor. Customers don't understand it. Dare I say, a lot of the compressor companies don't understand it, and a lot of the consultants don't understand it. So it's all become too hard, so people haven't gone there. So a Capex, which you need for any project to proceed, needs to have a justification for it to occur. So for energy efficiency work, this would be usually energy savings, but you could have your other goals like net zero 2030 corporate goals, and it needs a cost estimate. And the cost estimate needs that front-end engineering work to be done, and the document becomes the technical reference for the project to go forward with. So the feed captures when and how much energy can be recovered and can be used, and we've heard people already talk about the need for thermal storage to mix and match between what's available at night and what can be generated during the day. The temperatures and fluid and energy flows to allow the selection of your heat exchangers. So Selwyn and his colleagues can help you out with that. The concept, system design and an installation plan. How are you actually going to implement the heat recovery system? And that then leads you to having a cost of a bill of materials, so a price on how you're actually going to put everything together. So what's actually inside an air compressor and where all the heat flows? So this is a generic drawing of an air compressor. The air comes in to the top left there, goes into the air end, which is a compression module, gets compressed, and oil gets added to it. As we've heard with the refrigeration screw compressors, they'll inject oil there, same with an air compressor for most of them. The hot air oil mixture goes into what's called the separator tank, and the oil drops out and the air goes out to the aftercooler. Now the whole mixture is kept at around about 70 to 80 degrees, that oil going back in, and it's resultant high separator temperature, and that is kept up to 80 to 95 degrees. And that is to stop water condensing in the system. So you can't overcool the system, or else you'll get oil build up and you'll rust out inside your machine. If you go too hot, the oil will break down very quickly, and you can actually get separator fires and fires inside a compressor. So it's a bit of a balancing act. The compressor controls will shut down a machine. If it gets much above 95 degrees, it will start to alarm, and they'll shut down between 100 and 105. And that depends upon the compressor manufacturer. As far as where all the heat comes and goes, so about 95, probably 85 to 90% of the energy is provided to your main drive motor. Of that, 5% is lost as due to motor efficiency losses. If you've got a VSD, that'll add another 2 to 5% in the electrical losses going to the drive motor. And you've got your cooling fan motor as well. That will use between 2 to 5% of the compressor's nameplate power. So you'll reject 70 to 80% of the heat to your oil cooler and 20 to 30% to your aftercooler. Now you've heard people talk about, Selwyn was talking about 80 kilowatts, 80% of the heat going to the oil cooler. It is variable. It depends upon how the compressor is operating. And as you can see in that graph, the temperature being lost and the energy lost through your aftercooler varies with the temperature of the day and the humidity of the air coming into the machine. So if you've got wet, humid air coming into the machine, you've got to condense a lot of water, you've got to reject a lot of heat in your aftercooler. So the actual heat loads vary with the time of the day, with the season, and with how heavily loaded your air compressor is. Sorry, going the wrong way. So what are the temperature effects from recovering heat from an air compressor? Well, you need to maintain the temperature going back into your air end at that 60 degrees, 65, 70 degree sort of mark. I'll just bring up a little spotlight. Can you all see that? So around about this point, you've got to maintain that temperature. This is a heat you can recover from an oil flooded compressor. It's a mixture of your oil cooler and your aftercooler. Hence the reason why you've got your knee there. You're losing that heat from your oil, and then this is the remainder of heat from your aftercooler. You're losing some aftercooler heat to get to that point as well. The important thing is to have the colder the water coming in, the more heat you can recover. If your water coming in is too hot, you won't cool your air down enough. So you got your dryer and downstream equipment might be undersized, so you need to be aware of that. And for the best energy recovery, you need to go for a single pass of the water. So you need to get as big a temperature rise in that water as you can. And what I mean by that is to have that 70 degrees there in the water, if you've got, say, a 5-degree approach temperature in your coolers, the water coming in needs to be at 65 degrees. Now, if that water is only heated 5 degrees, it's going to go out at 65, and you won't be able to use that water again to recover the rest of that heat. Whereas you've got a 25 to 30 degree rise in that water, you can heat the water all the way up to the maximum it can do from that 65 degrees coming in. So it's really important to go with a single pass on your water, not lots and lots and lots of little passes, but a single big temperature wise. Yes, you've got a lot of low water flow, which can upset your coolers a bit, but it also reduces your pump power consumption, and you can go for smaller piping as well. So what do we actually need to put into an air compressor? There's lots of different bits and pieces you can do. Just bear with me. There we go. So how much energy can be recovered? You've got to log what your compressed air system's doing. You know how much power is going into the compressor, and that will give you an efficiency curve like you can see here. You've got to log your hot water system, so you know what your water flows are, your temperatures are, what your energy is in terms of gas and power, and also this will pick you up the mismatch between when your heat's being generated and when you're using, and if you're going to need hot water tanks. If your hot water system demands much bigger than compressed air heat output, you can go with a simpler design for a heat recovery system. So you need to be aware of all of that when you're trying to design your system. What you must really take account of in your model is what happens if you change how you operate your air compressor system. So this little graphic up here on the right, I've trotted it out a few times. This is a real system I logged many years ago. You've got two compressors, they run at different times of the week, and you can see for the same airflow, one compressor, the bigger one, was using twice the power of the smaller one. So if you had done a survey and you're modeling your heat recovery based on the bigger compressor, then all of a sudden you actually started being more efficient and ran the smaller compressor most of the time. The amount of energy you've got available for your heat recovery system has gone down quite a lot, and your economics might go out the window. Similarly, if you decide to do leak repairs, you might move from operating here to operating here. Now, these are fixed speed machines. If you've got a variable speed machine, it might actually be going somewhere down like this. So the model needs to be advanced enough to be able to provide the energy savings for the Capex justification to take you forward. So some of the design considerations from that, hot water system temperature rise, what do you actually need the hot water for? Are you going to fit heat recovery to all of your compressors, or to one of them, or to one of them minus your standby machine? Because often you'll have at least a standby machine in your compressed air plant. And as we've talked about, how you're going to operate your air compressor system. If you're only doing a reduced number of coolers, you can you have to optimize what machines you run so you can recover as much heat as you can. It's no point operating one machine that hasn't got heat recovery on it because you've just wasted your investment. Need for thermal storage. And then we get into the fun topics which some of the other presenters have talked about, which is the reliability and water quality factors, and how you design the system around that. What happens when you're running the air compressors, but you're not running your hot water? Air compressors will run all weekend and all week, more often than not, because they're supporting a lot of different services and they don't get turned off. But if you're only a 5-day-a-week production operation, what happens on the weekend when you've got no hot water demand available? What does the air compressor do? Similarly, what happens if your air compressors are down for, one of them's down for servicing? Say you've only fitted heat recovery to one of the compressors. When it's getting serviced 3 or 4 times a year, as they will, what happens with your heat supply system then? So you do have to have an alternate source of hot water for that backup scenario. And when you get into the insides of the compressors, you need to be aware that you're not creating extra stresses inside the machine, which can cause them to physically fail. So in some cases, you've got coolers, which are the air aftercooler and the oil cooler are physically joined together as one solid block of aluminium. If you were to take heat out of the oil cooler and not out of the aftercooler, you could cause temperature differences in your cooler, cause them to stress and crack and fatigue. So you need to be very careful about those sort of scenarios. Similarly, when you start adding extra pipes and coolers, what's the actual volume of oil that you are going to need to fill those coolers? The oil needs to be changed every now and then, a couple of times a year at least. The separator tank is also your oil reservoir, and that has a finite volume. So if all of a sudden when you start your machine, you put all of that oil into the hoses, you don't have any buffer volume and your machine will eventually overheat. So it's not just a fairly straightforward thing. You need to consider all of those considerations when you're designing the system. We've talked about the water quality and cooler fouling. Stefan did as well. Are you designing for a hard water area, or are you designing for a soft water area? You will get scale build-up. A lot of compressor companies, the OEM systems, won't sell a system if it's going to be heating the water above 80 degrees because they're scared of scale build-up inside the machine. So you need to design your system. If you're going to get scale, how are you going to get rid of that scale and keep your system working properly? Or are you going to just replace the coolers? Are you going to try and clean the coolers? Are you going to do both coolers, one cooler? So there's a lot to consider in that respect. And how tolerant is the water that you're heating from having extra heat added to it? So I had a customer where new compressors have been installed, 400 kilowatts of compressor water. They've got a big high pressure steam system, which is generating power before actually going out to the plant to provide process heat. And the customer said, no, I don't want water added to my boiler feed water because it'll overheat my feed water treatment system. He had big deionisation tanks. And if we were to go in after the DI system, it would potentially recontaminate the water. So how tolerant is the water to actually having it all installed? So can you physically fit the equipment to the air compressor? You need to get access inside and outside of the machine. Most compressors need access on at least 3 or 4 sides to get to the different filters and coolers and change your oil and check the operation of the machine. And there often isn't a lot of space between the machines to do that. It's typically sometimes as little as a metre, sometimes less, it should be more. So yeah, you need to consider all of that and physically fitting the system in, and what production windows will allow you to plan for the system to be installed. So if you have to do a staggered installation, it could be way more expensive and difficult than if you can do it, say, at an annual shut and do the whole thing then. So this is a suggested system. There are lots of different ways to do things, and it depends upon what you are planning to do. This system, the intent of this system is to give you the hottest water possible. So small water flows, and it's a generic designed for clean and soft water. You'd use this if the hot water system load was, say, 2 to 7 times that of the compressor waste heat, and it also considers the heat exchangers as siamese on the hot water side. So the main things you're adding is a VSD for the cooling fan. If you don't turn the cooling fan off, it will overcool the oil and still reject heat. So, and it's also direct power saving as well. If you can turn the fan off with a VSD, that's great. The VSD is controlled by the temperature of the oil coming out of the air end. If it gets too hot, the fan starts cooling. Easy. We've heard from Jensen about the needing to have split systems. We've got variable heat loads in the oil cooler and the after cooler. So run variable speed pumps that are controlled on the temperature coming out of those coolers. So you give the heat recovery system the first grab at the water. You run nice slow water flows through it, so you get maximum temperature rise. The pumps, you tell them what temperature you want to come out, and they run at that speed to give you that water. If you're getting too greedy and going too high, well, the fan will run. You'll get your hot water, but maybe not all of the heat. Once you're inside, you need to allow for the coolers, obviously, and the hoses for connecting the coolers in and out of everything, because yep, you've got to pipe the oil from here to there and the air from here to there, and also waterside check valves. If you've got, yep.
We've only got a minute or so left. I know you've got a few more slides. Is there anything we can just jump through in the last minute or so?
Yeah, I'll jump through quickly. So what'll be of benefit for a lot of people, this is budget pricing for different size machines for the different items that you need to retrofit. The slide before it provides you some information on the what's heat flow rates, what water flow rates you need for different size coolers. As I said, these are all flooded machines. This data is plotted off here, so it gives you an idea of what the cost for these major hardware items are, but you've got to add in your VSD cabling, temperature sensors, an allowance for people like me to help you design everything and put it in properly and commission it all. That's for the soft water system. Hard water system becomes a lot more expensive, depends upon how you do it. This is one approach I've taken and costed out. And you can see that goes up quite a lot. Quick case study, it was a boiler. Nameplate was 92% efficient. As we heard earlier, they're usually a lot worse than that, only about 70% efficient. They had a very cheap power bill, very cheap gas bill. You can see that the effective thermal cost of power, the cost of the energy in heat terms was about 3.7 cents compared to 12.2 cents for power. But even then, and going through the rest of it over here, we're saving around about $6,500 in power for major hardware of about $25,500 in major hardware costs. So this is only based on 5 days operation of the compressors, whereas this is a 7-day operation of thing. You'll get more heat back for the compressors. We don't have hard data on this system as we're planning to be logging it later this year. But it's a quick case study on how we can go through it. And everyone, yep, sorry, have a look at the slides afterwards when they come out next week. Yeah. So quick recap, Capex needs justification from heat recovery work. It's $1 saved. The gas was from a customer's bill was about 28% the price of electricity. That would be very fluid. That was off their February bill. As we know, the wholesale prices are going everywhere. Your feed provides the basis for your project cost estimate and your energy recovery estimates. So it's got your energy recovery data and demand modelling results, your heat exchanger selection data, your concept design, and your costed bill of materials. There we are, everyone. Thanks for listening. Sorry, I was a bit rattled going through that. Any questions?